In this video, we will implement a simple one-dimensional Fourier neural operator in JAX to solve the one-dimensional Burgers equation. For this, we will look at the theory of FNOs and the particular problem. We will obtain the dataset, investigate the dataset of the Burgers solution, implement the Fourier neural operators, including the spectral convolution. Ultimately, we will then train our network in a classical deep learning fashion, and then we can investigate its performance and see that it very closely matches the ground truth solution. We will also measure the error and investigate the claim of zero-shot super resolution. Let's get started. Hi and welcome to this interesting new video where we'll first start looking into neural operators. As you might have noticed, I'm using Google Colab here in order to get access to free GPUs. That's quite helpful in training these networks because we will have a bit of a larger network, so it's very helpful to have this accelerator performance. Aside from JAX, we will use Equinox as our deep learning framework and Optex for the gradient processing. So first of all, what are neural operators? So neural operators are mappings between discretized function spaces. That's quite abstract, but one particular example, that's also the one we will be doing in the video here, is the map from an initial condition of a partial differential equation to its solution at a later point in time. So here in this video, we will map the initial condition of a Burgers equation to its solution at a later point in time. We could also map from the initial condition to the entire spatio-temporal solution. So we have our, let's say for instance, a one-dimensional initial condition discretized. Then we would use that in order to map to this two-dimensional solution field, which has both space and time. This is one particular example. The one that was mostly emphasized during the early neural operator papers is a map from a function describing some sort of a parameters of the PDE. So for instance, if you have a heat equation and your diffusivity might not be homogeneous over the entire domain, but rather be a function. So for instance, if you have a PDE problem and in the left half of the domain heat spreads twice as fast as in the right half of the domain, then you could describe this with a function. And then whenever you change the diffusivity, you obviously have to resolve the PDE, and the neural operator in that case would be a mapping from the function showing the distribution of diffusivity to the solution of the heat equation, either just with one point later in time or with the entire spatial temporal solution, so the framework is quite flexible. However, what I think is by now the most important application of neural operators is as autoregressive time steppers. So this means that we would use it to map states or states of a transient PDE from one time step to the next one. So indicate this here with UH upper T to UH upper T plus 1. And it's called autoregressive because we would then apply the neural operator again to its own output. But that deserves another video. For now, we will just look at the simplest case to give you a starting point for FNOs. Okay, FNOs by itself are in the class of neural operators, but I think they are by now very much beloved because of their multiscale property. That means because we will employ convolutions in the Fourier space, also termed spectral convolutions, we can take into account global features, because the FFT allows us to transform into a space where we no longer have our actual state, but we have the frequencies or the waves within that space. And this allows us to actually have a view of the entire domain. Because for instance, if you compare that with classical convolutional architectures, their receptive field, so for instance, if you use a kernel size of 3, is just one point to the right and one point to the left. And if you then stack convolutions in a conv net, then you increase your receptive field, but your receptive field is always limited by the depth of the network. And as such, if you, for instance, have very fine discretizations, let's say 1,000 degrees of freedom in a one-dimensional discretization, then you can think of how much depth of a convolutional network you'd need in order to see the entire domain. And FNOs kind of do that more or less for free by employing the FFT, which is a very efficient algorithm. I already mentioned that neural operators in particular allow for the solution of a whole parametric family of PDEs. This is, as mentioned, it's a bit of an difficult terminology, but for me personally, I think the most important application is as autoregressive time steppers, and here we just map state to state. Then FNOs also claimed something very interesting, which they called zero-shot super resolution, and that means if we train a network on, let's say, 256 degrees of freedom, it also works on a solution which has multiple of that degrees of freedom. And this is an inherent property of the spectral convolution. I think that's a very nice thing, and we will also see that later on. Okay, let's first talk about spectral convolutions. The idea behind spectral convolutions is that in general a convolution with a very wide filter is just a multiplication in the Fourier space. So let's assume we have our current state in network A. So this can, for instance, be something on, let's say, 256 degrees of freedom, and we could also have more than one channel. Then we basically do a Fourier transformation, and not just any Fourier transformation, because here we will restrict the FNOs to real PDEs, or PDEs whose solution are real functions. So we can just take the real valued Fourier transformation. So this kind of saves half the computation. If you want to learn more about the RFFT, I have a video linked up here. But what does the RFFT do? It takes, let's say, a 256 dimensional vector. So let's say we only have one channel dimension, and maps it into a vector which is approximately half that size. So in our case, it would be 129 entries of complex values. So it will have 129 entries, but each entry has both a real and an imaginary component. And we use this A hat vector to then perform the actual spectral convolution, which is the multiplication with a complex valued weight matrix. But we will not do it for all the 129 entries, but we will only do it for a specified number of modes. So for instance, typical number would be something between 8 and 20. So we only have weights for the first 20 modes in our solution, but we have weights for the first 20 modes in our solution for both the real and the imaginary component. So this will be a complex valued multiplication. And of course, we also map channels here. So this is quite a large matrix. So actually it turns out that it is a 3-axis tensor with the dimensions being channels out, channels in, and modes. Then once we have obtained the result of the spectral convolution, we'll have the original values for the higher modes. So for everything that is above entry 20 in our transformed vector, and this one will be just set to 0. And that also makes sense because the modes in our Fourier space reflect the frequencies. So that means the lower modes refer to smaller frequencies. So if you take a look at this illustration they do here, so they take the state, apply the Fourier transform, and then this gives them a collection of waves. So they have the first mode, which is one period of a sine or a cosine, and then they have the second mode, it's 2 periods of a sine or a cosine, and so on and so forth. And then they make this complex valued multiplication. Here they call this R, and this then gives them only the upper 2 modes because the lower ones are zeroed out and they are modified. So for instance, they indicate that here by them being flipped, but of course we can scale them and so on and so forth. But what we do not have anymore after this is we don't have any high frequency information anymore. So this is cut off. And to some extent, this aids us in our multiscale architecture because with these modes we already have the global information in. So these modes usually refer to very localized high frequency information, but this is the mode we actually want for the global information. So once we then have the transformed modes, we will apply the inverse Fourier transformation. So this is the IRFFT, and then we will get this, I denoted it here as A tilde, the result of the spectral convolution. This spectral convolution is kind of a layer that we have to implement, and its parameters or its learnable parameters will be channels out, channels in modes, but each of this entry in this 3-axis tensor is actually a complex value. So if you count in real parameters, we actually get twice of that. And we will also allocate them as real values. This is just the spectral convolution, as also indicated by the schematic that I took from the original Liedal paper, is that an FNO consists kind of like ResNet style of multiple stacks of the spectral convolutions, but each spectral convolution also gets a bypass. So once we have the state, we have one path that goes through the spectral convolution and another path that goes through a regular convolution. But this is not just any convolution, it is a 1x1 conv, or one-dimensional case, it's just a 1 conv. That means a convolution with kernel size 1. So there's actually not a true convolution, it's just a scaling of each state. And you can think of it as a way that maps the channels. So if our computation in here modified the number of channels and we needed a bypass, then this would take care of the modification of the channels. And then ResNet style, we will add it up and ultimately apply a nonlinearity. And this gives us a Fourier layer from which we will use a couple of. So in the example here, we will use 4. And then additionally, we have what they term P and Q, which is a lifting and a projection layer, because our input is usually not of the number of channels that we actually want. So let's say, for instance, we have a 2-channel input. We would operate at 16 channels within here and keep them also constant, no modification. Then this lifting layer just maps 2 to 16 channels. They are also 1x1 linear convolutions. Okay, let's go down. This is essentially our FNO, and just to have that here in code as well. So these blocks, or the FNO block, is an activation function applied to the spectral convolution result plus the 1x1 convolution applied to the input. The particular example that we solve here is related to the Burgers equation. That's a nonlinear PDE problem. It is a transport problem. We will also look at the solution to these problems shortly. It is discretized on a domain that goes from 0 to 2 pi. And it also has periodic boundary conditions. We will fix the diffusivity level, so this is new here, to 0.1. We will use the dataset created by the authors, which fixed that to 0.1. And then we'll get a dataset that has 2048 initial conditions. So these are states at time equals 0, discretized on 892 resolution points. And we will get that together with the solution at time level 1. So this also then has 8,192 spatial points. And now our goal is to learn the mapping from the initial condition to the state at time 1. And additionally, we will also give the mesh as an input to the FNO, this state concatenated with the mesh. And the output is then just with channel 1. A few technicalities. So we will not train on the full resolution. So first of all, that would be very costly, but we will use the higher resolution later on to investigate the claim of zero-shot super resolution. What we will do is we will use only 256 degrees of freedom, and as we will figure out, that is also totally fine for learning that problem here. Our FNO is quite a big one, to be fair. So it has 16 modes and 64 hidden channels. So that gives us quite a lot of parameters. We will train it deep learning style with a dataset that is shuffled in each epoch, and we will fix the batch size to 100. 200 epochs in total with the Adam optimizer and a learning rate of 3e-4. So the original paper by Lee et al. Also came with a reference implementation in PyTorch. So this code that I will show you here is a little bit deviated from that code. I intended it to be an educational reduction. If you find any differences that are really crucial, please let me know in the comment. I would also be very happy to learn that. Okay, I now connected to a GPU on Google Colab. You can change the runtime type by one of the drop-down menus. It's the weakest GPU you can get, but is sufficient for our purposes here. First, I want to install the Equinox package, which is not installed on Colab by default, by saying %pip install Equinox. And this should install it into our environment. And then we can already start with the import. So we will need JAX. Then we will need jax.numpy as JNP. We will import Equinox as EQX. Then we will import optex. We will import matplotlib. So matplotlib.pyplot as PLT. And then we will also import from the typing package the callable type and the list type. And we will also need SciPy. Okay, let's execute that. Okay, next up, we want to get the dataset. And this dataset is around 600 megabytes. It's also hosted by the original authors on Drive, but there's a nicer link that is more smoothly from MathWorks, so the creators of MATLAB, that host that file, and it's in the .mat format. And we can get it by using the exclamation mark. So this is kind of an escape character in Jupyter, so that we will call it from the bash shell. And this should download the dataset. This will take a couple of minutes. Okay, with the dataset downloaded, we can read it in by saying data is scipy.io.load metrics. And then just give the file name, and file name is burgers data r10.met. And then shift enter, loads in the dataset. This will also take a little bit. And this dataset can be accessed like a dictionary, and within there we have A and U. And this is by the terminology of the authors, the initial condition and the solution at time equals 1. So we will do data and then index it at A, comma, data indexed at U. So shift enter gives us A and U. And just as a quick side note, the authors like to use this A and U because they more generally focused on the case where we have the constitutive parameters like the diffusivity to the heat equation as the input function. Okay, let's look at the tensor shape. So A.shape is 2048 by 8192. And this is the number of samples, and these are the spatial points that we have available. Okay, let's just take a look at this by plotting it. So let's do plt.plot on A.0 and give it the label of initial condition, and then plt.plot on U at 0. So the corresponding solution also has the same shape. We will index with 0 the 0th sample. And let's also give it a label and say after 1 time unit. And then let's activate the legend in our plot. There we go. Let's plot this. And there we go, the solution to the burgers problem. I think it's also nice to have a crit in here to nicely analyze that. So what do we see? The initial condition is a periodic function. So that means the value on the left hand. So here it is not plotted over the real mesh. It's just the index number within the array. But on the left end of our data, we have the same value or a close value to the right end. And what we actually see as an initial condition is a Gaussian random field. You can think of it as something noisy in a sense, but smooth noise. So it's not like high frequency noise, but it's kind of a low frequency noise. And then in orange, we see the solution after 1 time step. And this also matches the burgers equation. So you can think of a burgers equation as an advection problem. So it moves the solution, but positive solutions are moved to the right and negative solution is moved to the left. And here, as you see, we have kind of, or maybe let's start here, we have a negative mountain or a negative region, and this is moved to the left. But next to it being moved, it's also smoothed. So that means we do no longer have these high frequency features in there. The solution is way more smooth, but it is moved. Okay. Yeah, so far so good. Our goal is now that to learn a mapping between the blue and the orange curve by taking into account a lot of samples that we have here. Okay, so before we start coding the FNO, I want to actually create the dataset as we will then need it in the training. And for this, we will add first a channel dimension to our data. So add channel dimension, and that is because whenever we work with convnets, we need to adhere to certain conventions when they are implemented, and here basically we have a singleton channel dimension which is not within the data, and then we will get the classical format of batch channel spatial. Okay, how can we do that? By saying U is U indexed at all of the 0 axis, and then jnp.new axis, and then again a colon, and A is the same, or actually we should have it done the other way around to have A first. So A is A indexed colon jnp.new axis colon. Then let's create the mesh. So the mesh is from 0 to 2 pi. So we will get mesh equals jnp.linspace from 0 to 2 times jnp.pi, and the number of entries we want to use is u.shape at -1. So this refers to the number of spatial points, and this is 8192. Okay, let's create that, and then we can also quickly take a look at how the solution actually looks like when we plotted together with the mesh. So let's have mesh, A0 and mesh, U0. And now we have the correct x-axis. So, okay, so yeah, we see we need to index it here at 0 as well to take out the channel dimension we just created. But once we do that, we actually get the same functional form, but now the x-axis is correct. So we go from 0 to 2 pi. Okay, now we want to concatenate the mesh to each of the A's. How can we do that? So right now the mesh is just a vector with 8,192 entries. You can also see it highlighted here. So we need to extend dimensions, but not only that, but we also need to repeat it over the samples because each sample has the same mesh. So let's call this mesh shape corrected. And this one is mesh indexed at jnp.new axis, jnp.new axis, and then colon. But as said, this would just give us a mesh with 2 singleton dimensions in the beginning. And in order to get the 2048 dimensions in the very first axis, we will repeat it and say jnp.repeat on this mesh with u.shape of 0. So these are the number of samples we have. And then we want to repeat it over axis 0. Okay, what does it do? Take axis 0, which right now would just be a singleton dimension, and repeat it u.shape at 0 times, which is repeated 2048 times. Then let's create A with mesh. And A with mesh is jnp.concatenate of A and mesh shape corrected. And we want to concatenate over axis 1 because axis 1 is our channel axis. And of course, this should be mesh. And now if we take a look at A with mesh shape, we should see it is 2048 to 8192. Okay, let's extract our data and train points. This is again to follow the Lee et al. Paper. So we will take train x and test x by doing A with mesh and index it at the first 1000 samples. So we will do 1000 samples on training, and then we will use the following 200 samples for testing and validation. So 1000 to 1200. And then let's do train y and test y with u indexed at the first 1000 and then u indexed at 1000 to 1200. Okay, there we go. So this is everything prepared for our supervised learning problem. Next up, let's implement the FNO. And in the typical fashion for how to build these networks, we will create modules of the component and then composite larger components. So let's first start with probably also the crucial component of the FNO, that is the spectral convolution. So let's say spectral conv 1D, and this will be a subclass from equinox.module. Then we need to define its attributes. So it has real weights, and earlier we talked that the parameters of a spectral convolution is this 3-axis tensor, at least in 1D, and this is complex valued, so it has both a real part and an imaginary part, and I want to save both of them separately because the imaginary part is just a real tensor and the real part is a real tensor, and then we will reassemble the complex tensor when we need it. So let's attach a type. So the real weights are a JAX.array. Then the imaginary weights are also a JAX.array. And then we also want to set the in channels, so how many channels the incoming state has, which is an integer. The out channels is also an integer, and the number of modes is also an integer. Next up, let's define the constructor, so def __ init with self, and then what is the signature? So we want it to hand over the number of channels that go in, the number of channels that go out, the number of modes, and then as a keyword argument, I want to hand over the pseudo-random number key, which is required for the reproducibility in JAX. And then what does it do? So first let's save all the attributes. So let's do self.in channels equals in channels and self.out channels equals out channels and self.modes equals modes. Okay, next up we need to initialize the real and imaginary components, and as always with network initialization in deep learning there are very established rules for classical convnets and MLPs. So here we will just follow the spirit that with the larger the transformation is between the channels, the smaller we have to initialize the weights. And this can be reflected by just saying that we use a scale to our uniform limit by 1.0 divided by in channels times out channels. So this also follows the reference implementation from Lee et al. Okay, then since we need to allocate or draw both real and imaginary weights, we need to split our key into a real key and an imaginary key by doing jax.random.split on the key. And then we can draw our weights by saying self.real weights equals jax.random.uniform and hand over the real key. And then we need to say the shape. And this is now this 3-axis tensor with in channels, out channels, and modes. And then we can also set the limits of the uniform distribution with min value being minus scale and max value being scale. Or if you want to be precise, plus scale. Okay, cool. Let's copy that because it looks very similar for the imaginary part. So let's say self.imag weights is all the things are the same. The only difference is that we will use the imaginary key. And that's already it. This is our constructor. Let's implement the forward pass by implementing the call function, which takes self and x. So x in that sense is the state. So terminology vary a bit. So earlier I called it a, now it is x. And let's first extract channels and spatial points from x. So say channels and spatial points is x.shape. And now you might wonder, typically in conv-based networks we have batch channel spatial, but here we follow the paradigm within Equinox that by default all networks are single batch. And I think this is a very nice convention, but of course it breaks a bit with some things you might have learned within PyTorch or TensorFlow. So the elegance here is that x is always single batch, so means it is just a 2-axis tensor. And then later on we will use the JAX vmap primitive to extend it, and then it will automatically batched. So in that sense we also never have to worry about batch dimension, which I think is very handy. Okay, so let's go back to the theory part and look what the spectral convolution actually does. So step number 1 was to transform A into Fourier space using the real valued Fourier transformation. So let's do that. And then we essentially get x hat, which is jnp.fft.rfft on x. And this rfft already batches over the channel dimension. So it is a one-dimensional real-valued Fourier transformation. And it looks at the very last axis, which is the spatial axis, performs the FFT over it, but keeps or batches over the channels. So in that sense, the returning shape of x will be spatial points, integer divided by 2 plus 1. So the shape of x hat is channels, and then spatial points, integer divided by 2 plus 1. So in the case we have 256 spatial points, like we will use for training later on. The shape of x hat is the number of channels. Let's say it's 16 channels, and then 256 divided by 2 is 128, plus 1 is 129. Okay, but we're not interested in the full x hat for now. We will say something x hat under modes, and this will be the subset of modes that we will consider. For this, we have to index it. So we will say x hat indexed at all channels and then up to self.modes. And again, the modes represent kind of the frequency. So the lower entries in our mode vector correspond to the first period, the second period, or so on and so forth. So a sign with increasing number of periods, the higher the modes we go. So we will only consider the low frequency information. Then we will assemble the weights. So because we saved the weights in their real and imaginary component, let's assemble them to a complex valued array by saying self.realWeights plus 1j. So this is the imaginary unit in Python, multiplied with self.imaginaryWeights. And then basically we need to do our batched multiplication. And for this I want to implement a separate function, but first let's imagine we already have it and call this out fft under modes being self.complex multiply 1d of x fft under modes and weights. And for this, let's create another function in our spectral convolution and call it like we called it here. Oh, sorry, this should be x, not x fft, but x hat. And let's also call that hat. Okay. Okay, let's get to the creation of the function. And this shall be this complex mult 1d. And this takes self and then x hat and w being this weight vector. And now we need to think about it. So x hat as said has channels and then this number of spatial points by 1. And now we have it reduced. So we can also say the shape of x hat under modes is channels and then self.modes, because we only have self.modes left. And now we want to multiply it with an array which has in channels, out channels and modes. So the output, which we actually have out hat under modes, shall then have a potentially changed number of channels. So to be precise, these are in channels and this is also an in channel. So in that sense, we can say the shape of out hat under modes is, sorry, this should also be an is here. So is out channels and then self.modes. Okay, and the way to go here is to use the Einstein summation convention. There is a very handy tool in JAX NumPy to do that. It can be a bit tricky, so let me walk you through this. So we will use einsum, and then we need to provide a string of what we want to do, and then provide the operands, and say x and w. Sorry, it should be x hat. The axes are the in channels, and let's call it I, and m the modes. W has 3 axes. It has in channels, out channels, and the modes. And the shape of the result that we want to have is out channels and modes. So what will the insum do? It will multiply the 2 arrays and sum over the indices that do no longer appear in the output. So we will sum over the in channels and add the out channels, and we will batch over the modes. Okay, cool. This is this complex multiplication. Okay, this out hat under modes now reflects essentially our a tilde hat 0 to k. And now we have the leftover modes. And for this, we can just allocate a 0 tensor and then put the out hat under modes in there. Okay, let's do out hat and say this is jnp.zeros of, now we need to hand over the shape, which is self.out channels and then x hat dot shape at -1. So because this out hat has the shape out channels and then spatial points integer divided by 2 plus 1. So let's also add that here. So shape of out hat is out channels and then spatial points integer divided by 2 plus 1. And we also need to fix the correct d-type, because by default it would be a real value tensor. So we will say that its d-type or data type is x hat dot d-type. So if this is a complex float 32, then we also want this to have complex float 32. But right now it's just a zeros tensor, and now we fill in the number of modes and say out hat equals out hat at, and then at all channels, and then up to self.modes.set out hat under modes. So the reason we don't use indexing on out hat and then assign is because JAX does not allow array mutation, and this is our way around that. And then ultimately last step is to get out by saying chainp.fft.irfft on out out hat. And then since we used real valued Fourier transformation, it is ambiguous on how many exact spatial points we had. So we need to inform that and say n is spatial points. So then return out, and this is our spectral convolution. Okay, let's keep going. Next up is an implementation of the FNO block. Let's say class FNO block 1D. Again, subclass from module. And this FNO block has 3 attributes. So first it consists of a spectral convolution, which is an instance of the spectral conv 1D we just created. And then we also have this bypass conv, which was this 1x1 conv. And this is a classical, we would say, classical windowed convolution. So equinox.nn.conv1d. Oh, sorry, this is wrong. It should be conv1d. Then we also have an activation function, and this one is a callable. That's the reason we imported callable, because when we define the attributes of a data class, which an Equinox module is, we need to always attach a type to them. And so this one is a callable. Okay, let's create the constructor. So the constructor for that class takes self, and then we need to define the in channels, the out channels, the modes, and the activation function. And also we need to have the key for reproducibility again. So then let's first split the key, because we need a key both for the instantiation or the initialization of the spectral convolution as well as the bypass convolution. So let's do spectral conv key, and bypass conv key is jax.random.split the key. So then we will get self.spectral convolution is equal to the spectral conv 1D with in channels, out channels, modes, and then the keyword argument key, which is the spectral convolution key. Then we also have our bypass convolution, which is equinox.neuralnetwork.conv1d applied to in channels, out channels, and now we need to define the kernel size 1, and then we also provide the key, which is our bypass convolution key. Okay, so we set the kernel size to 1. So this maybe I just want to highlight here. So the kernel size is 1. This gives us the 1x1 convolution. So I mean, 1x1 convolution is a terminology for 2D convolutions, for image convolutions. So here it's just a 1 convolution. So this convolution maps in channels to out channels, but it also has a bias. Okay, then let's also save the activation function by doing self.activation is activation. This is the constructor. Let's move on with the forward pass. So the call method, which takes as an argument self as well as x. And then what does it do? It returns the activation function applied to self.spectral convolution applied to x plus self.bypass convolution applied to x. So it's very simple forward process, and the spirit is close to a ResNet-like structure. Okay, let's shift enter that cell and move on. And then finally, after a lot of preparation, we can implement the actual FNO. So let's say class FNO 1D is another Equinox module. And what does it have? So it has a lifting layer. This is in order to adjust the channel dimensions, which is again equinox.nn.1d convolution. Then it has FNO blocks, which is a list of FNO 1D, of FNO block 1D. And this also shows why we imported the list typing. So it indicates we have a variable number of blocks in here. And then we have the projection layer, which is equinox.nn.conv1d. And we don't save an activation function separately because we have the activation within the FNO blocks. And this is also one way it differs a little bit from the reference implementation, but I think having the activation in the blocks is a bit more straightforward. Then let's continue again with the constructor. So define __init takes self, and then what are the arguments? So we will do in channels, out channels. Then we need to define the modes for the spectral convolution. The width is like the hidden channel dimension, and we need to define the activation. And then I also want to define the number of Fourier blocks, but in order to match that with the reference code, I want to set this to 4 by default. And then again, a keyword argument for the pseudorandom number key. Okay, then let's initialize all the components. So first of all, the lifting layer. For this we will again, for this we have to split our key. So we will do key and lifting. Key is jax.random.split key. So we will override our global key we use here and create a specialized one for the lifting layer. So self.lifting then is equinox.neural-network.convolution1D on in channels. So it takes the number of input channels and maps that to the width, which is our hidden width. And then it shall be a 1-by-1 convolution. So 1 here, and the key is the lifting key. Okay, then next up, we need to initialize our FNO blocks. So let's first start with an empty list and say if self.FNO blocks is empty list. And then for I in range blocks, we will do the following. So first we will split the key again. So key and subkey is jax.random.split on the global key. And then we can do self.FNO blocks.append and place in an FNO block by constructing our FNO block with width and width. So in that sense, the FNO blocks that we have don't change the channels. So we will keep this hidden channel constant. Then we have modes, and we need to hand over the activation function. And as the key, we will use the subkey. So this should create our 4 FNO blocks by default. And then ultimately we have the projection layer. So again, split the key in key and projection key. Although of course this split here would have not been really relevant, but let's be more general and also split the key here. And then say self.projection is equal to equinox.neural-network.convolution 1 dimension on width to out channels with a 1-by-1 convolution again. And the key is the projection key. Okay, so far so good. This is the constructor. Then let's go over to the call function, which also takes self and x as an input. So again, x being a very general variable name. We will first lift the channel dimension. So self.lifting applied to x. And then for the FNO block in self.FNO blocks, we will apply the FNO block and say x equals FNO block applied to x. And then ultimately we will project the hidden channel dimension down to the out channel dimensions and say x is self.projection on x and return x. And this is our FNO. So then we can instantiate our network and say FNO is the FNO 1D. And then we have 2 input channels. That was because we had both the state concatenated with the mesh. Then we have 1 output channel, which is just the state or the 1 variable associated with the Burgers equation. So the y you saw in the plots earlier. And then we want to use 16 modes and a 64-dimensional hidden channel. The activation function shall be the relu, and as the key, we will use a fixed key and say jax.random.pseudorandom key and just use 0. Okay, that's the FNO instantiated. And we see we have an issue, cannot set attribute projection. I think, yes, there's a typo. Let's see if that works. Okay, great. That solves the issue. So now the instantiation works. Okay, before we now can do the training, I want to implement a data loader because by default, JAX does not come with one. And there's also none in Equinox, but it's very easily implemented. And I just want to copy that in here. Just let us quickly go over it. Takes a key because the dataset is shuffled and pseudo-random numberness is deterministic in JAX and reproducible. So we need a key. Then we have the X and Y dataset that we want to shuffle. We have the batch size. and then we create our batches. This is the permutation, which essentially shuffles the data set, and then we just iterate over the batches that are within the data. So if we have 1,000 data points and we choose 100 batch size, we essentially have 100 mini batches, and then we just return the indexed data points. And in case you have not seen this yield before, this is essentially what makes this function a generator, so we can use it as part of a loop header. Okay, this is the data loader. Then the following cell will be all about the learning. So what do we need? So first we need to define a loss function. Here this will be a bit more tailored toward FNOs, but if you are interested in a simpler example of how to do training loops with Equinox and JAX, I also have this simpler video linked up here. Oh, and I just noted I forgot to uncollapse this top bar. Okay, let's continue with the loss function, which takes a model. So this is the current state of the model during the training, as well as X and Y, which are the mini badges on the input and the output. And then we first make a prediction by calling the model on X. But now we have to be careful because X is now of the shape mini batch size, channels, spatial. So our model was only intended for single batch usage, or where we don't have a batch dimension or axis at all. And in order to make our model work on a batched input, we need to transform it with jax.vmap. So jax.vmap on the model and then apply to X gives us the batched prediction. Then the loss is essentially jnp.mean on jnp.square of y prediction minus y. So it's a very classical supervised loss. And then ultimately we can return loss. Then let's define an optimizer. And as mentioned, we want to use the Adam optimizer from Optex package with the constant learning rate of 3e minus 4. And then we can initialize optimizer state by saying optimizer.init on equinox.filter on FNO with the filter rule Equinox is array. So as said, if you want more detail on why we do that, please watch the more simple video. But in general terms, what happens here is for Equinox, all networks are callable pi trees. And in order to be proper JAX pi trees, they need to be made pure. Also, the activation function needs to be stripped. And this is what the filter function does, or this filter transformation. Okay, then we can define a step function. So this is essentially the core of our algorithm or of our training loop, which advances the model parameters by one iteration. So it takes a model, it takes an optimizer state and X and Y. And then we first transform the loss function by automatic differentiation by saying equinox.filter value and cred applied to the loss function and then called on the model and X and Y. And this returns the loss and the gradient. So the loss will be a scalar value and the gradient will be a structure, so in essence a pi tree of the same type as the model. So this is essentially another model, but instead of having the parameters in each of its leaves, it actually has the gradient values in the leaves. Then we can use the optimizer to create an update. Call this updates and new state. And this is optimizer.update on gradient, state, and model. And then we will use the update to update the parameters and say new model is equinox.apply updates on the model with the updates. And then we return the new model together with the new state as well as the loss. Okay, and since this is the core step or the most computationally expensive part in our training pipeline, we will JIT compile it. So let's use the decorator and say add equinox.filter JIT. And we need the filtered version of JIT because we work with Equinox models here. Okay. So let's go down and then do the actual training loop. And I want to record the loss. So let's create an empty list with and call it loss history. And then we also need a shuffle key. So generally a key which makes the dataset shuffling reproducible. So let's say a shuffle key and use jax.random.pseudo-random number key. Then we will train for our 200 epochs. So let's say for epoch in range of 200. And then in each epoch, we need to split the key again, because it's actually beneficial to shuffle differently in each epoch. So we will override the global shuffle key and create a subkey by saying jax.random.split on the shuffle key. And then we can essentially say for batch X, batch Y in dataloader applied to our dataset. So we will hand it over the subkey for reproducibility, then the train X dataset, as well as the train Y dataset. And we need to define a batch size, and the batch size shall be 100. Okay, then in each update step, we will do make step on the FNO together with the optimizer state, as well as batch X and batch Y. And then this returns the new model. So we will just override the FNO variable, as well as the new optimizer state, which we will also override. And then we also get back the loss. And this loss we can append to our loss history. So we will do loss history.append loss. And then before we run it, I want to do a couple of modifications. So first of all, it would be nice to have a progress bar to follow the training progress. So let's go up and change the imports here. And I want to use a TQDM. So let's say from TQDM, and there's this nice shortcut, which is called Auto Notebook, which loads the correct TQDM meter based on the environment. And we will import TQDM, and then Shift Enter executes that. And then we can place the TQDM around the outermost loop, which gives us a very nice training progress. And then here we are still training on the full data set with all its 8,192 degrees of freedom. And as mentioned at the beginning, that's quite a lot. So it is sufficient to reduce that. Here we want to do a 32-fold substepping, and we can do that by just substep here. So we will use the ellipses to just index the very last axis, which was the spatial axis. And with a : 32, we can actually substep. And we will do the same on our targets, also the 32 substepping. Okay. And then next to the loss history, I also want to record the validation loss history. So in each update step, we will also compute the validation loss. So let's do that before we actually update the model to get a loss that is on the same parameter state as the other training loss that was computed. So let's compute validation loss by doing loss function on the model applied to test X and also substepped. So ellipsis and then : 32, as well as test Y on ellipsis : 32. So we will just use the entire test or validation data set to compute the validation loss. So let's return the validation loss as well. So this will also be a return here. So validation loss, and we can append it to the validation loss history and record it for later. So val loss. And with this, we should be good to go to finally execute our training loop. So with Shift Enter, this should run. So first we will have a little bit of time for the compilation, and there we go. Now it runs. So this is a reasonable training time, actually quite fast, around 20 to 30 seconds on this Google GPU here. Okay, then let's visualize the loss history. And for this, we'll use matplotlib. So plt.plot on the loss history. Let's attach the label being training loss, and then we want to plot the validation loss history, and let's attach the label val loss. Then I want to activate the legend. I want to set the Y scale to logarithmic and activate the grid. Let's run that, and then we get a perspective on the training loss. Okay, here we go. So in the beginning, we start at around, let's say 5e-1, so at 0.5 training loss. And then eventually we are able to bring down the training loss to 10 to the -5. The validation loss also goes down, but it looks that after these 2000 update steps, so 200 epochs with 10 mini batches each, we are somehow converged. Okay, let's take a look and test what that network produces. So for this, let's plot the prediction of the network. So let's do plt.plot on the test x, and let's choose one particular. Let's for instance take 1, so not the 0 sample but the first sample. And then since the x input is now with the 2 channels, so it has both the mesh as well as the actual state. So we want to extract the state, so we will index at channel 0. And then I also want to plot the substep solution. So let's do substep 32, and we will attach the label being the initial condition. So this is one test input for the network. Then let's plot the ground truth. So plt.plot on test y indexed 1, 0, : 32, and attach the label ground truth. And then do plt.plot on FNO called on test x indexed at 1. So when we index at 1, we remove the batch dimension, so we then still have an 2-axis tensor only, so we don't need the VMAP transformation on FNO. But ultimately, we need to extract the one channel out of it, so we will index at 0 and say label is FNO prediction. Then let's activate the legend as well as the grid. Then computing that takes a bit of time, and hopefully we should see something. Oh yeah, actually, yeah, I see. We forgot the substepping for the test. Okay, so this should be 1 : to get the channel, both the state as well as the mesh. And then of course we need our substepping, so 32 substepping. Okay, let's see. Okay, here we go. So we have in blue the initial state again. So as mentioned earlier, this is a Gaussian random field. Think of it as a low frequency noise. And then the typical Burgers behavior, if we have negative values, so below the 0 line, they move to the left. So the ground truth and the FNO prediction correctly move that mass to the left. And if it is positive, that mass is moved to the right. And this is all reflected. And overall, we also see that the FNO correctly predicts the modes. So in that sense, so correctly predicts that the qualitative behavior is like less exciting in the actual solution. And if you see the element-wise match, we see that the FNO prediction and many points closely matches the ground truth. So let's plot the difference. Let's go to a next line, and here we want to plot plt.plot on FNO applied to the test x indexed 1: substep 32, and then at 0 minus test y 1, 0 and substep 32, and give it the label difference, and then activate the legend. Let's see what we get. So we get that the difference between is noisy. So the largest difference, if you think, is around 0.006. So it's about 2 orders of magnitude smaller than the magnitude of the solution. But I mean, if you look at it closely enough, you see that there are some points where it is off. So you might even argue that the FNO produces something that is has a bit more energy in the higher modes, so indicating that it is a bit wavy here. Okay, so this is the prediction of the FNO on one particular sample. Now we want to investigate 2 more things. First, I want to look at the 0-shot super resolution, and this basically means that we trained at 32 substepping. Let's try a different substepping and let the network predict. So this is the experiment 0-shot super resolution. And if you're not familiar with the term 0-shot, that's a terminology in machine learning you typically use. If you get a feature or like kind of a performance metric or something is good at something without seeing that in the training. You would have 1-shot super resolution if you would give it one example of that. But here 0-shot super resolution means that our FNO is capable to extrapolate or to generalize to higher resolved domains. Qualitatively, we still have the same function on these higher resolutions, but we have more degrees of freedom. And for instance, think about training a classical convolutional network. That would fail because a convolution or a convolution network applied to these particular PDE problems would encode the discretization size, so the delta x. And if we have higher resolution, the delta x is smaller. And on top of that, as was mentioned earlier, the convolutional networks have a receptive field that is bound with the resolution. So if we increase the resolution but do not adapt the depth of the neural network, our effective receptive field in terms of physical units gets smaller. But long story short, let's just implement that here. And for this, I will just copy most of the plotting call. So let's copy and paste that here and replace 32 with 4. Here we go. And then plot that. And here we see, so we should see something. Yes. So you notice that we have higher resolution because we do not plot the mesh. So actually we plot here the index in the array. And here you see it goes until 256, and here it goes until 2048. And qualitatively, we get a very good prediction again. So you could argue it's more or less the same prediction, but that's a nice feature of the FNO, right? So that you can give it more resolution and it still works. Of course, this higher resolution has to be on an equidistantly sampled grid again. That's a prerequisite for using the FFT ultimately. But oftentimes that can be the case. And for those scenarios, it's a very nice feature. Let's also plot the difference function here. And copying the call again. And then use 4 and 4. And there we go. Here we have the difference function. Okay, last point, I want to compute this error that is also mentioned in the paper. So for this, let's first give this a heading and say compute the error as reported in the FNO paper. And I want to compute this error on the highest resolution. So the error on the 8192 it is resolution. So for this, we will first make a prediction by the network by saying JAX.vmap on FNO applied to test X. So this then gives us our result or the prediction for each of the samples we have in our test dataset. Then I want to define a function I want to call relative L2 norm. This one takes a prediction as well as a reference. So the reason I'm implementing a function now is because I want this to be a function that operates on one sample, such that we can compute that loss and then we can map that over the entire samples in the test prediction and the test data set, and then ultimately can compute the mean. So this just takes one sample here. So what does it do? It first computes the difference norm between the two by using jnp.linalg.norm on prediction minus reference. So this by default will resolve to the 2 norm. So it will basically take the difference and then square all the entries and sum them up. Then we will do the ref norm, which is jnp.linalg.norm applied to reference. And then this just returns diff norm divided by reference norm. So it's kind of a normalized expression. And that's also quite nice in using these relative norms, because then the domain size and the discretization does not play a role. Because usually what you have if you want to discretize functional L2 norms is that you get a scaling of L divided by N. So you get a mean squared error that is also scaled. And you can avoid all this confusion, whether taking the mean or taking it not, or multiplying with the domain size or multiplying it not, by just considering relative norms. Because if you computed the ref norm the same way as in the diff norm, and in both cases you would use the same scaling factors, so some factors multiplied it, and then you divide by each other, those would just cancel. But importantly, this norm command, I incorrectly said that earlier, so it will square all the entries, sum them up, and then take the norm. So it is, the square root of the sum of the squares, you might say. Okay, long story short, let's map this over the test prediction and the test Y. So let's say relative L2 set is JAX.vmap of relative L2 norm applied to the test prediction and the test Y. And let's execute that, see if that works. So this takes a bit because we are vmapping the FNO on a lot of batch dimensions, so 4 seconds. And now if you take a look at this L2 set, its shape should be 200, because we still have 200 samples in our test data set. So basically this is an error metric for each of the entries. And in order to aggregate that, we will take its mean. So jnp.mean on the rel L2 set. And here you go. So this is a quantity, it is 0.0095. So let's say it is roughly 1e minus 2. So that's roughly 1e minus 2. And that is very close to the number that is reported in the paper. So I now want to summarize a bit. So what do we do? So first we looked a lot at the theory of FNOs. And I just want to remind you a bit that in more general terms, neural operators are mappings between discretized function spaces. And that can be a lot. Here we looked at this example of mapping from an initial condition to a solution at a later point in time. But I think by now, one of their also very important application is autoregressive time steppers. We will look at that in a later video. The key idea of FNOs is to employ a spectral convolution with help of the FFT. And as such, we get global features, or we can do global convolutions. That's very helpful for PDE problems, which have a very wide receptive field, or have in the worst case, the entire state is relevant for just advancing to the next state. So this can be reflected with the FNO. And in essence, if we have the spectral convolution, an FNO is just some sort of a ResNet. Okay, this is also what we implemented. So first we got ourselves the data set, looked at it and saw that it is a collection of Burger solutions at time unit 1, and we saw that what the Burgers did, moving positive mass to the right and negative mass to the left. We concatenated the mesh into the X dataset, since this follows what was done in the FNO paper. And then we implemented the actual FNO by its modules. So first a spectral convolution, then an FNO block. And with the FNO block, we essentially built a ResNet, and then we were able to instantiate that, built a dataloader, implemented a loss function and a training loop with our JIT compiled step function. We saw our loss go down, the training loss and the validation loss both converging here, and saw in the prediction that the FNO prediction closely matched the ground truth, and it was able to do, so the FNO was able to do zero-shot super resolution. And we measured the error in a similar way as was done in the FNO paper and got a value that was very close to their paper. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed this video. It was a long one. There is more coming on neural operators and also, as mentioned, autoregressive neural operators, which I think is a very interesting topic. And also stay tuned for more videos on spectral methods, because I think the FNO has very strong similarities with spectral and pseudospectral methods that are very widely used in PDE solutions or numerical PDE solvers. For now, here you will see similar videos, and I hope to see you in one of the next videos.